Good day, everyone. Today, I will be discussing how to determine natural frequency for single degree of freedom systems as part of the course 22088 for torsional vibrations. My name is Dr. C. Sennamrikkannan. I am Associate Professor in the Department of Mechanical Engineering at SVC. Before going into some practical problems, let me discuss about the simple pendulum. A simple pendulum which is going to be oscillate about this mean point. Let me take the simple pendulum length is L, which is having a mass M. So what is the force acting here is it is the weight mass into G, because of which force the pendulum will return back to the equilibrium position is it is going to be the force which is acting towards our left. What is this force when we resolve W is nothing but if it is mass is swing at an angle theta, then this will be equal to mg sine theta. So restoring force for the simple pendulum is mg sine theta. If you want to take the torque, restoring torque for the same simple pendulum, then it is going to be force into radius. What is the radius here? The radius here is nothing but the length of the rod. So the restoring torque is nothing but force into the length of the rod, which can be nothing but mg sine theta into L. Let me see an application oriented problem. In this system, we are going to calculate the natural frequency. We have to consider that mass of the rod is negligible when compared to the mass m. Let me see and analyze the system. So, in the last slide, we discussed that the force which is acting on the pendulum, which, which is restoring the pendulum to the mean equilibrium position, we calculated. Keep that in mind. So, let me go for the Newton's method. The applied torque, that is going to be applied torque. Here we have to write it as J. Since it is going to be the rotational motion, it is J theta double dot K, which is going to be equal and opposite to the restoring torque. Let me find out what are all the restoring torques. First torque is it is going to be the due to because of the mass component, and the next one is due to because of the spring component. So we already discussed what is the formula which is for the mass component, that is which is pulling the pendulum to the mean position, which is minus mgl sine theta. Similarly, for the spring, we have to look into it. For the spring torque, it is going to be torque. So once again, it is going to be force into radius. This force is in the form of stiffness into the deflection. Then it is going to be radius. So we have to see that what it is. So here the spring is having the stiffness K into deflection. It is deflected to this extent. So what is this? Because if it is at the initial position, then there is no deflection. If this is going to be the initial position, no deflection. So here it is deflected this much. So this deflection is going to be given as A sine theta. So here this deflection is A sine theta. So K A sine theta into R. R is nothing but this one. So here it is A. But once again, it is going to be deflected. It is at this theta deflection. So this one is going to be A cos theta. So we can write it as R is A cos theta. If the deflection is very small, we can write it as sine theta equal to theta. cos theta as 1. So we can rewrite this equation as j theta double dot equal to minus mgl theta. So it is mgl theta. That is, this is changed into theta alone. Cos theta will be changed into 1. So then minus of k a theta into a 1. Okay, so rewriting once again, j theta double dot equal to this minus mgl plus ka, the minus will come outside theta. So we will put everything on the one side, then it will be j theta double dot plus mgl ka into theta equal to 0. So from this, we can come to a conclusion that this is the stiffness part, this is the mass part. So what is the natural frequency? The natural frequency is nothing but omega equal to root of k by m. If we write it, it is going to be omega equal to root of mgl by ka square. Here it is a 2a. So here it's a square divided by, it is going to be g. So this is our natural frequency of this system. Once again, the j also can be written in the form of mass into radius of gyration, that is ml square. So that you can change this j, substitute this j equal to ml square. With this natural frequency of this given system is over. Let me continue in the next slide. What will be happen to the same system having two springs? So in this second problem, it is going to be the extension of the previous problem. We can see that here the mass is connected with two springs. One is on the left hand side, another one is on the right hand side. The left hand spring is having the distance to the pivot point A. Right hand spring having a distance to the pivot point, it is B. So let me recall all the things. So whenever we are going to write it for the torque system, the applied torque is going to be equal to J theta double dot. It is acceleration. Once again, the J can be written at ml square. So if I'm substituting that, the applied torque will become as ml square theta double dot. What is the restoring torque? Restoring torque is due to because of mass component and the spring component. So the mass component already we discussed in the previous two problems. That is, it is nothing but minus mgl sine theta. Similarly, what is this torque due to because of the spring? What is going to be the left hand spring? Just you recall from the previous slide, it is nothing but your the stiffness into the deflection, it is sine theta. So this is the deflection part, a sine theta. So this comes as the force into the radius. We are writing the torque. So the radius is nothing but a cos theta. Similarly, we have to write it for the next spring on the right hand side. It is k. Thus it is going to be here. It is going to be, it is b sine theta. The deflection at this point is, it is b sine theta. So stiffness into the deflection, which will give the force into the radius part is b cos theta. So in this case, once again, we have to rewrite sine theta equal to theta, since for the small deflections, cos theta can be written as 1. So in that case, what we have to do, the entire equation restoring torque can be rewritten as minus mgl theta minus ka square theta, because cos theta will become as 1 then minus kb square theta. So first equation is this, second equation is this. Now what we have to do, equate the two as per the Newton's law. So ml square theta double dot, put all these things on the one side. So plus mgl plus ka square plus kb square into theta equal to 0. Now we know that this is going to be the J part, this is going to be the stiffness part. So omega n equal to root of k by j. So let it like this. What is the stiffness part? mgl plus ka square plus kb square divided by the j, polar moment of inertia, can be written as ml square. If this is going to be the unit of radians per second, if you want natural frequency in terms of it, then you take omega divided by 2 pi. We will get natural frequency in terms of hertz. This problem is quite different. You see that here masses are moving linearly. Similarly, here this mass also moving linearly. Okay, again, we can't able to do the problem in the same way. That's why I taken this problem, even though it is look like same. But we have to take this system and analyze it using the energy method. It is the best method suitable for this kind of linear vibration system, and it is more complex. So it is easier to solve using the energy method. So let us start. So this is an indicator mechanism. Here you can see that a arm which is pivoted at this point O as a mass moment of inertia I. So you can clearly see that it is, they are telling mass moment of inertia I. They are not telling it is polar moment of inertia. Okay, so it is a linear vibration only, purely. Okay, find the natural frequency of the system. Okay, with this meanings, that is what they are telling in this, use having the regular meanings. It is K means stiffness, okay, M is mass. Let me focus on the energy method. What energy method is telling? Energy method is telling us total energy is going to be constant. What are the total energies? It is kinetic energy plus potential energy in the system is going to be constant. So let me first write the kinetic energy acting on this system. What is the kinetic energy formula? Kinetic energy formula is of mv square. Okay, so the potential energy formula for the spring is going to be of k x square. X square is, it is displacement. Okay, we have to appropriately choose whether here the displacement in the form of A or B. So appropriately we have to choose. That's all. Other than that, it is very easiest. Just we have to substitute half m velocity square. Similarly, half k square. So let me go for that. Okay, kinetic energy first. Let me start. What is the kinetic energy? It is going to be half mv square. So in that case, let me go with the mass, first mass, then the first mass is this, then it is the kinetic energy equal to half m v square. V square in sense, here what is going to be that it is going to be denoted in terms of velocity. So if it is x, x is here, it is c, okay, and also if it is deflected, you have to see that it will deflect. So the deflection is given as theta. So here also the deflection will be theta. Okay, so what is this deflection? It is c theta. If it is theta is differentiated, then only we will get the velocity. So c theta dot. Okay, so of m v square instance, here we have to put c square theta dot square plus this is m1. Similarly, we have to write it for the second mass of m2. Here the deflection is for a, so it is going to be same fashion. Here also the mass is deflected. It is deflected for theta. Okay, so what we have to do, it is going to be a square theta dot square plus. Now we have to come to this indicator mechanism. Indicator mechanism arm. Okay, so for the arm, we have to it is in the form of a rotation. So it is not like that we can write it as half mv square. It is nothing but half. Since it is in the form of a rotational movement, pure rotational movement, mass is to be replaced with mass moment of inertia. V, we know that V means linear velocity. Then here it is angular velocity. We have to write that. So it is going to be theta dot. Means okay, theta dot square of mv square. So this is the first equation, kinetic energy equation. Next equation, we have to go for potential energy. Okay. For potential energy, it's everything purely with respect to the spring only. Okay, so we are having three springs. For each spring, we have to write it. This is this one. Okay, that is potential energy of each spring is half into stiffness into what is x. X is nothing but for each and every spring. We know that very important. That is, it is given as radius. Here it may be a. Okay, if it is deflected by theta is, then what we have to write? This deflection is equal to a theta. Okay, for K2 it is A theta. For K3 it is B theta. For K1 it is going to be C theta. So accordingly we have to write. So potential energy is nothing but half Kx square, is it not? So we have to put that half stiffness for the first spring K1. The stiffness for this spring, what is the deflection is going to be C, is it not? So it is going to be C theta square. Similarly, we can write for half K2 is going to be K2 is connected with A deflection. So A theta square plus half K3. The K3 is connected with B deflection. So you can see that it is B distance. K3 is at B distance. So we can write at K3 into B theta square. Okay. So what we have to do in order to solve this, so let me start with continuing the problem. That is, we actually derived kinetic energy and potential energy for the systems. So kinetic energy is to be given as, you refer from the previous slide, that is I'm rewriting it, theta dot square plus of, it is m1 c theta dot square plus of m2 a theta dot square. Then we have to go for the potential energy. Potential energies we derived in the previous slide of k2 a theta square plus of k1 c theta square plus of k3 b theta whole square. Now, as per the energy method, what we have to do, potential energy plus kinetic energy equal to constant we have to put, and also to find out the natural frequency we have to differentiate this with respect to the time. Okay, if we are differentiating this with respect to the time, okay, what will happen? Okay, let me start. Okay, let me have it. So if I am differentiating this, what I will get, I will write it in this side. If I am differentiating of I theta dot square, I will get half into 2 into I. First theta dot I have to write it. Okay, then if I differentiate with respect to time the velocity, I will get theta double dot. So 2 will get cancelled. Okay, similarly if I am differentiating of
m1 c theta, this is square, this is square, separate it. So I am differentiating it of m1 c square 2 theta, and theta dot will come. So 2 will get cancelled. Okay, you can see that everywhere the velocity component will come into picture. Okay, so velocity will be differentiated into time, means it will get the acceleration. Okay, so after differentiation, the kinetic energy can be written as, how to write the kinetic energy? It is going to be I theta double dot theta dot plus m2 square theta double dot plus m1 c square, it is theta double dot. Everywhere theta will come, that is the velocity will come. Okay, already velocity is there, plus, okay, we have to write the kinetic energy differentiated terms. So the similar way only. Okay, so this half will get cancelled. Okay, I will write it here. Okay, once again, just half k2 a theta square instance, what will happen, of k2, 2 will come outside, a square, then theta will be there. Okay, then if this is going to be displacement is differentiated with respect to time, means we will get velocity here once again. So what will happen, 2 will get cancelled. Okay, so what will happen, at last we will get k2 8 square, is it or not? So here we will write it, this is going to be the potential energy is differentiated, means then what will happen, it is going to be k2, okay, a square. Okay, so there will be velocity and theta also will be there. Okay, it's displacement, so velocity and theta, okay, both will be there. Then we have to write it as k1 c square velocity theta plus k3 b square velocity and theta. Everything should be equal to constant, but if the constant is differentiated, it will be equal to 0. Then we can cancel this velocity which is everywhere. Okay, I commonly taken here, outside here also, if it is commonly taken, everywhere it is there. Since the velocity is not 0, like that only we are taking it out and it is removed. Okay, now we can rewritten the equation in the form of theta double naught. Okay, we are rewriting it, it is going to be, so high plus m1, okay, c square plus m2 a square theta double dot plus k2 a square k1 c square plus k3 b square equal to 0. That is, here commonly displacement will come out. We know that this is the stiffness component, this is the mass component. So omega n equal to root of k by m, you know that. So that one we have to substitute it. With that we can come to this end of the problem, that is we identify the natural frequency. So I can write in the form of k1 c square k2 a square plus k3 b square divided by, we have to write I plus m1 c square plus m2 a square. So with this we determine the natural frequency. So this is going to be natural frequency formula. Okay, we have to write k divided by m. So students, so this kind of problem is very important to understand. You understood well. If you are having any doubts, ask in person. Thank you.